Time travel debugging, but for keys. Time-based key value store is a Pattern Mastery 100 favorite because it blends hash maps with binary search. It's asked at Meta/Amazon to see if you can store version data and pull the value as of a timestamp, fast. Today we'll lock it down with basic and produce clean O-login. Lookups. We must design a class with set key, value, timestamp. Store the value for the key at timestamp. Get key, timestamp. Return the value for the key with the largest timestamp less than or equal to given timestamp. Return if none. Input guarantee. For each key, timestamps in set are non-decreasing. That means we can keep a sorted list per key. Naively scanning backwards at get is on and too slow. Because per key timestamps are sorted, we can binary search the last timestamp not exceeding the query, O-log_n, time. We'll store dict key, list of, timestamp, value, or two parallel lists, append on set, and use bisect_right on get. Keep store. Dict str, list tuple int, str. Set, store key. Append timestamp, value. Get, binary search that list to find the rightmost pair with t less than or equal to query. If none, return. Time complexity for this approach is O1 for setting values and O-log_n, for getting values using binary search. We only append values when setting, and when retrieving, we use binary search on a sorted list of timestamps. We use a method called binary search with bisect. Each key stores a list of timestamp value pairs. New values are always appended, so timestamps remain sorted. To retrieve a value at a given timestamp, we perform binary search to find the latest timestamp that is less than or equal to the given timestamp. If such a timestamp exists, we return its value. Otherwise, we return an empty string. This approach is quick, efficient, and perfect for a time travel dictionary. In our Java implementation, we first create a map where each key points to a list of timestamp value pairs. Think of it like a folder for each key, containing a timeline of saved versions. When the time map is initialized, this storage is ready to hold every key we see. To set a value, we check if the key exists. If not, we create a new list for it, like adding a brand new folder. Then, we append the timestamp and value to the list. Since timestamps are always increasing, we don't need to sort, we can just append. To retrieve a value, we first check if the key exists. If not, we return an empty string. Otherwise, we fetch the list of versions for that key and prepare for binary search by setting left and right pointers. We also keep a temporary answer in case we find a valid timestamp. Binary search begins by repeatedly cutting the range in half. At each step, we calculate the middle index safely without overflow. If the middle timestamp is less than or equal to the desired timestamp, it's a valid candidate. We store its value and continue searching to the right for a potentially later timestamp. Otherwise, if the middle timestamp is too large, we search to the left. After the search stops, we return the best value found, or an empty string if none exists. Each timestamp value pair is stored in a simple inner class, like a little data box holding both pieces of information together, and that's how this algorithm works. It organizes each key's values by appending them in order, then uses binary search to quickly jump through time and find the closest version stored. Efficient, simple, and elegant. Timestamps are guaranteed to be in increasing order, so appending is O1. Binary search makes retrieval O-log_n, making this approach perfect for building a reversible or historical key value store. Now that we've implemented our time map class, let's verify that it behaves correctly with a sequence of operations. This test will show how we can store key value pairs at different timestamps and retrieve the most recent value for a given time. We'll walk through the input operations, see how values are recorded and retrieved, and confirm that the output matches the expected results. Let's test our time map using this input. We perform a sequence of operations. Initialize a time map. Set key foo to bar at timestamp 1. Retrieve the value of foo at timestamps 1 and 3. Set key foo to bar 2 at timestamp 4. Retrieve foo at timestamps 4 and 5. Here's why the solution works. The algorithm stores all values of each key as a list of timestamp value pairs. When get is called, it finds the largest timestamp less than or equal to the requested timestamp using a binary search. Step by step, after set foo, bar, 1, the list for foo is 1, bar. Get foo, 1, returns bar because timestamp 1 exists. Get foo, 3, returns bar because the latest timestamp less than or equal to 3 is 1. Set foo, bar 2, 4, adds the pair, 4, bar 2. Get foo, 4, returns bar 2. And get foo, 5, also returns bar 2 as the most recent value less than or equal to 5. And that is exactly what the program outputs. Null, null, bar, bar, null, bar 2, bar 2, bar 2. This confirms that the code is functioning correctly and passes this test case. So our implementation is correct. The algorithm successfully handles timestamped key value storage and retrieval, efficient, accurate, and reliable. Our implementation is correct. It accurately stores multiple values per key with timestamps. It retrieves the latest value less than or equal to the requested timestamp using binary search. It passes the given test case and is efficient for larger inputs. This approach is O1 for setting values because we just append pairs, and O log n for getting values using manual binary search. We use a method called manual binary search. For each key, we keep a growing list of timestamp, value, pairs. Since timestamps are added in increasing order, the list is already sorted. When we call get, we perform manual binary search to find the closest timestamp less than or equal to the one requested. We then return the value at that timestamp, or an empty string if no valid timestamp exists. This gives fast lookups while keeping the implementation simple and predictable. In our Java implementation, we first create a map that links each key to a list of timestamp value entries. Think of each key as having its own timeline. When the time map object is created, we initialize this map to prepare empty storage. To set a value, we check if the key exists. If not, we create a new empty list, like opening a fresh folder. We then append the timestamp and value to the list. Since timestamps always increase, the list remains sorted automatically. To get a value, we first pull the list of all saved versions for that key. If the key doesn't exist, we return an empty string. We then set up our binary search window with left and right pointers and keep a temporary result variable to store the best match so far. Binary search runs until the two pointers cross. At each step, we calculate the midpoint safely. If the mid timestamp is less than or equal to the requested timestamp, it's a valid candidate. We update our result and move right to search for a possibly later valid timestamp. Otherwise, if the mid timestamp is too new, we move left to search earlier ones. After the search finishes, we return the best matching value, or an empty string if none existed. Each timestamp value pair is stored in a small helper class, which simply holds a timestamp and its value together in a neat container. And that's how this algorithm works. It stores every timestamp in order by appending, then uses manual binary search to quickly find the best matching timestamp. Efficient, simple, and elegant. Timestamps are always added in sorted order, so no reordering is needed. Binary search guarantees fast lookups, even when each key has many timestamps. The worst-case lookup cost is O log n. This is the time map, storing values with timestamps. Set saves a value, get retrieves the latest value at or before a timestamp. Like solution 1, we track boundaries, here, timestamps, to get the correct value efficiently. For key foo, timestamp 1 bar, timestamp 4 bar 2, get at 3 returns bar, the latest before 3. Output, null, null, bar, bar, null, bar 2, shows it works. Simple, accurate, and reliable. Breakdown recap. We needed to design a class with two main operations, set, which stores a key value pair with a timestamp, and get, which retrieves the most recent value at or before a given timestamp. If there's no valid timestamp for that key, we simply return an empty string. Assess recap. A naive way would be to scan backward through all stored timestamps each time we call get, but that's too slow. Since timestamps for each key are always added in non-decreasing order, we realized we could use binary search to find the correct version efficiently. That gives us a clean O log n lookup instead of ON. Structure recap. We stored all data in a dictionary that maps each key to a list of pairs, each pair containing a timestamp and its corresponding value. When setting a value, we just append it to that list. When getting, we perform a binary search to locate the rightmost timestamp less than or equal to the query time and return its value. Implement recap. After implementing the class with set and get methods, we ran it on LeetCode, and it executed smoothly without any errors. Check recap. We tested multiple scenarios, overlapping timestamps, missing keys, and boundary cases, and all produced the correct outputs. The main takeaway? Time-based storage problems reward structure and search efficiency. By pairing hash maps with binary search, we built a clean, scalable solution that handles versioned lookups in logarithmic time.